Hello everyone, my name is Lucas and today I'm going to present you my paper about use of rockfall dynamic barrier as hydroelectric power plant access protection. The goal of this presentation is to share as much relevant information about this project as 5 minutes allows me, so let's get started. Emery Border Power Plant is situated at the city of Cubatão, São Paulo, Brazil. Due to military reasons, this power plant is built inside an artificial cave and has a main access path, used as people and vehicle access. There is also an emergency exit designed to be used at only extreme cases. In 2013, a block of approximately 2 tons fell right before the main entrance, threatening the workers. This event called the attention of the power plant administration, that immediately suspended all the activities of maintenance at the powerhouse entrance roof, in addition to start planning a viable economic solution as well as environmentally friendly. Based on these observations made during on-site inspections, was clear that another rockfall could suddenly happen, exposing people at risk. To guarantee safe conditions for those who use the facilities, a solution was compulsory. The power plant is situated at an outstanding area of Mata Atlântica, the most threatening tropical forest in the world. Thus, it's mandatory the solution applied delivers the minimal environmental impact as possible. Solutions as false tunnel and barriers have been considered on the project, and the dynamic rockfall barrier showed itself as the most cost-effective solution as well as environmentally friendly. A rockfall dynamic barrier works using its capability of deformation to dissipate boulders' energy, without being necessary a huge structure. For this reason, the rockfall barrier uses less material when compared to this false tunnel and delivering the same level of protection. The design is aimed to choose the most convenient barrier regarding the impact energy, impact height, a possible second impact using barrier's residual height, and the barrier deformation. The first step to design a barrier is to define the possible trajectories of the blocks and calculate its velocity and impact height. This first analysis is carried out through a commercial software called rockfall developed by Rock Science. Once the velocity and height is defined, the barrier is designed using the Italian standard UNI 11211, Part 4 from 2012. This standard foresees the calculation method that shall be used, as well as the safety factors applied on the design. The barriers are standardized kits, testing according to the specific guideline. When this paper had been written, the guideline was called ISL2020-37. However, this guideline was superseded by an EAD guideline. The EAD foresees the test procedure and production standardization to ensure the barrier performance. Barriers can be designed to receive one impact, which is called maximum energy level, let's call it MEL, and cell, that is the service energy level, which foresees multiple impacts in lower level of energy, enlarging barrier safety margins. Once there are many losing blocks on the slope, close to the powerhouse entrance, the barrier was designed on cell. The designed block energy was 728.37 kilojoules, with a height of impact of 1 meter. This value requires a barrier RMC 200 from Macaferri that has 2000 kilojoules in MEL and resists to 730 kilojoules at cell. In case of impact, a deformation expected was about 5.25 meters. The installation process was carried out with many challenges, such as difficulties on the area access and barrier staking out, which had to be slightly changed since there was higher level difference between the posts in some sections. With all foundations ready, the barrier was installed in less than 1 week, and the work was delivered in December. 7 months later, in July, the barrier was inspected to ensure that all the components were working as it should be. Thanks for your attention.